Hey there. In this video we are going to look at how replacing x with negative x or y with negative y in the equation of a function causes a horizontal or vertical reflection in the graph of that function. When you're talking about functions in mathematics, the word reflection means essentially the same thing as it does in the everyday usage of that word, i.e. an image of a function over a line or in a line. You can say either one. And in this situation here, this red function, I've got two reflections here. I've got a vertical reflection over the x-axis, and I've got a horizontal reflection over the y-axis. And as I move this around here, you'll see that the reflection changes as well. Right? And I can actually put it right up to the line that I'm reflecting it over, or I can even put it through in mathematics. In the everyday usage in a mirror, you can't really put your face into the mirror and see the reflection, but in mathematics we can here. So I can actually put this on the bottom here, right? If this red function is on the bottom, the reflection's up above. And then the horizontal as well. That green image is across the y-axis there, all right? Now, as you can see, in a reflection, the orientation of the graph can change and the location can change, but the shape doesn't change. It's upside down or turned left to right or something like that, but the shape is maintained. We're going to look a little more closely now at reflections of functions, numerically and graphically, or in other words, with tables and with graphs. We're going to use as our base function here the basic square root function, y equals square root of x, which you may or may not have seen before, but I think you'll recognize some of the numbers involved in this first table here. And then we're going to make two changes to it. We are going to change it from y equals square root of x to y equals negative square root of x. And we're also going to change it to y equals square root of negative x. And we're going to complete the tables just by substituting in those values, right, for x in every single case there. And in the interest of time, we will just have a look at what those numbers are right now. There we go. So in the first table here, the basic square root function, you're just substituting a number and taking its square root. Now this is the positive square root. It does not say plus or minus here. It's just the positive square root. So square root of 0 is 0, square root of 1 is 1, 4 is 2, square root of 9 is 3, and so on down there. Now, the change that when you look at this, and the reason I have these highlighted here, is because they all are exactly the same as these numbers, except they're opposite in sign. And the reason they're opposite in sign here is because when you substitute these numbers in here for x, you still take the square root. Say, for instance, here with 9, you still take the square root. Square root of 9 is 3, but then this negative in front turns it into a negative 3, and so on there. So when you change this to negative square root of x, it changes the sign of all of those y values there. Whereas in the second one here, you're changing the sign of the x value before you take the square root, because that negative is inside. This is replacing x with negative x. And as you can see, the reason I've highlighted the x values is because those are the ones that need to be different here. To get the same y values, you need to have x values that are opposite in sign. If the first thing you're going to do is change the sign of the x value, you can't start with all these positive values, because when you put them in there, you'll have a negative, and you can't take the square root of a negative. But if you start with negative values here, say if you put in 16, if you substitute 16 in here, you get square root of negative 16, which is just square root of 16, which is 4. If you're going to change the sign of all the x values, you need to start with negatives there, all right? So if you want to think about what's happened in this first change here we made, this negative outside the function causes all of the y values to be opposite in sign. Whereas in the second one here, where we're putting the negative inside, we've replaced x with negative x. All of the x values have to be opposite in sign in order to get those same y values. Now we'll look at what's going on here graphically. You can create the graph for those three functions just by plotting the points and drawing a smooth curve through them. In the interest of time here, I've already got those graphed. What you're going to get when you do that is this. You get those three curves there. Our original base function here is a curve that looks like that. Now, you may not have seen this before, as I said earlier, but those values you actually likely have seen in previous math courses, because you had the point 0, 0, 1, 1, you had 4, 2, you had 9, 3. Those points sound a lot like the points that you had if you've graphed parabolas before. And in fact, these two pieces together, you've likely seen that shape before. It's very much related to a parabola, to a quadratic function, but that's a lesson for another day. If this is our base function here, and in the second table, what we did is we had this negative outside. Essentially what we were doing is multiplying by -1. All of these positive y values became negative. What that does on the graph is it causes this vertical reflection. When there's a negative outside like that, it causes all the values that are y values that are positive to become negative. Now this graph doesn't have any, this red graph doesn't have any y values that are negative, but if it did have values that were negative, they would also change sign. So if they were down here, they would end up there, as you'll see a little later on. The second one here, this function, when we look at what's happened there, this is the one where we replaced x with -x inside, and the x values were the values that were changed. So these points over here have reflected over to here. So all of those points, like that point that was, say, 4, 2, turned into -4, 2, right? The x value changed sign. Whereas for this one down here, it's the y value that changed sign, right? 4, 2 became 4, -2, right? So if we're going to sum up what happened here, y equals -x has been reflected vertically. And we should say where the line is that it's getting reflected over. The line it's getting reflected over in a vertical reflection is that x-axis there. So you can also say that it got reflected over the x-axis. Whereas the other one, y equals square root of -x, has been reflected horizontally. And again, you can say what it's been reflected over, but it's been reflected over the y-axis, right? That's where sort of the mirror is for that reflection. So we can say here, over the y-axis. I know it's a little bit weird and sometimes confusing for people that when you reflect something vertically, it reflects over the x-axis, whereas when you reflect something horizontally, it reflects over the y-axis, because in your mind you associate y as vertical coordinate. If you're looking at a reflection this way horizontally, just like if you look at your reflection in the mirror, you're looking horizontally, but the mirror is vertical on the wall that you're looking in. If you had a mirror on the floor, if you're staring down at the mirror on the floor, you'd see a reflection looking straight down vertically, but that mirror would be sitting flat on the floor. So that's why it's opposite like that. Next, we're going to have a look at some graphs that have been reflected and try and write an equation to represent those graphs. So in this first case here, we have our original function is this red dotted line here, this bizarre function, and we're just calling that f of x. And then we have this other function, it's been reflected, and it's called g of x. So what we're going to do is write an equation for g of x in terms of f of x. So if you look at it, you can tell that it's been reflected horizontally, right? This is where the mirror is, if you want to think of it that way, right? Because any point on one side here, this point has been reflected over to there, this point's been reflected over to there, and so on, right? This point's been reflected over there, right? A negative value becomes positive, positive values become negative. This point right here is reflected over to there. It's a horizontal reflection, so we have to take x and replace it with negative x. That's how you get a horizontal reflection to happen. And to do that, so we're going to say g of x is equal to f of x, except I need to, instead of putting x there, we need to put a negative in there. When you do that, you get that g of x equals f of negative x. That's an equation representing that function. Whereas in the second one here, if we look at it, this is pretty clearly a vertical reflection. That's the mirror again, the line that it's reflecting over. If you look at it, say this point right here is reflected up to there, that negative value becomes positive. This positive value becomes negative. It's the same distance on the other side of the line that it's reflecting over. Any point you pick here, right? Let's pick one that's kind of a nice number to work with, right? This one is 7 above here, so it ends up on the other side, 7 on the other side of that line, right? An equal distance on the other side. So that one's been vertically reflected. And so for that, we have to multiply the function by -1. We need a negative outside of the function. So maybe we can just say multiply f of x by -1, right? So if we're calling this one g of x again, I guess I could have used something different there, but I used the same thing twice. G of x equals negative f of x. You need that negative outside to cause a vertical reflection. Now, before we move forward here, we're going to bring in a new term, and that term is what you refer to as an invariant point. The word invariant point, when you talk about a transformation, are points that don't change as a result of that transformation. And when you have reflections, you do have points that remain unchanged after reflections. So in these pictures above here, if you look at it, in this first one, as we said, it's a horizontal reflection. The mirror is vertical. The line of that it's reflecting over is vertical. And that's where you're going to find invariant points, because this point right there, 0, 1, doesn't change. 0, 1, in a horizontal reflection, it's the x value that changed, but if you change the sign of 0, it remains 0. Whereas any other point, right, pick this point right here, that point, right, that point is -4, 1, right? That point moves to over here, 4, 1, right? The x value changes sign there. Whereas if it's 0, you can't change sign because 0 is the same whether you put a negative in front of it or not. All right, so that point is invariant there. So we can say there's one invariant point there, which is 0, 1. Right, so we can say points where x is 0. And then the second one here, invariant points, it has a few of them. Anywhere along this axis here, that point didn't change, that point didn't change, and that point didn't change. There's actually 3 invariant points there. It's points along the line of reflection again, that line right there. Those points are invariant. Any points on the original function that are on that line are invariant. And it's for the same reason here, right? Because along there, the y value is 0. So those points that you have there are approximately, we're just going to have to estimate this a little bit here. It looks to be like about, I don't know, 0.3 or something like that. Who knows? 0. And the second one looks like around about 3.2 maybe, 0. And then that third one looks like about, I don't know, 5.7 or something like that. Might have been good if I had made it so it was whole numbers, but that's okay. You get the idea. The common thread there is that all of those points have 0 as a y value. So invariant points in a vertical reflection are points where y is 0. We're going to look now at a function that we're given the graph for, the function f of x, and we're going to draw the graph of the transformed function y equals negative f of negative x, and actually you're going to see since both changes have been made, in other words, we've replaced x with negative x, and then we've multiplied this function by -1, so there's a negative outside there, it's going to have had both reflections done. Maybe we'll note here, that's a horizontal reflection, and this is a vertical reflection as a way of abbreviating it. Abbreviations like that, HR and VR, are good ways to abbreviate that. So it's reflected both ways, so basically change the signs of both x and y. So you have a couple of approaches here. One is you could just look at these key points and then just look at the coordinates and then switch the signs of both of them because both reflections have happened. So for example here, this point, -2, 1, and that is going to go to, that's going to change to, since we have had both reflections, the -2 is going to turn to 2, and the 1's going to change to -1. And so you could go about doing it that way. I won't do the whole way there like that, but 2, -1, it means it's going to be over there. You could do that for all of the points, and you'll find that you'll get the shape of that graph. You could also just reflect them visually on the graph both ways. You could say this point, if I do a horizontal reflection, it's going to be an equal distance on the other side. This is 2 away over here, so it's going to be 2 away over there. And then if it does a vertical reflection, it's going to be, since it's 1 above here, it's going to be 1 below, and you end up with that point in the same place. So either way you do it, if you look at the values numerically or if you kind of work with it graphically, either way is fine. And what you're going to find is this point, on a horizontal reflection, it doesn't change. It stays there because it's on the axis, right? Because it's horizontal reflection changes the x-coordinate, so that point that is 0, -3, it stays as, the x-coordinate stays as 0, but then on the vertical reflection, it's 3 below, so it's going to be 3 above. And you can do the same thing for all of the other ones. Right, so if we look at this one, if we're going to do this one visually, horizontal reflection means it's going to be on that side of that axis, equal distance, and then it's going to be same up here, so that one's up there. And then this one, if we do this, do a horizontal reflection, it's 4 on that side, so it's going to be 4 on that side. And then it's 1 below, so it's going to be 1 above there. And then the last one here, I'm doing it more graphically now, but you could do it the other way as well, right? You could say I have 5, -1, and I know for a fact that then that's going to change to -5, +1, and then just graph that one. -5, +1 is going to be there, right? So if you connect these, so it goes like that. You don't actually need the points there. I mean, you can take the points away, but it doesn't matter if you have them there. So that function is going to look like that. You can tell that it's been reflected both ways. One way is that this little short little piece here is now on the left side instead of the right side. And this low part of this sort of scoop looking thing is on the top now instead of the bottom. So it's been reflected both ways there. And what you might notice is when you reflect something both ways, both across the x and the y-axis, it looks as though it's just been rotated 180 degrees, which it has. If you reflect something both ways like that, horizontally and vertically, it results in just a rotation like that. Next, we have a little bit more complicated of a function here that we're given as an equation, and we are going to write an equation for a reflected function, both in the y-axis and in the x-axis, and simplify it. So, starting with this one here, if we have, that's our function we're working with here, I am going to use g of x to represent my transformed function. So if I want to reflect it over the y-axis, that is actually a horizontal reflection. So what I need to do is I need to take x and replace it with -x. And so g of x is going to be the same as f of x, but instead inside here, I'm going to change this to -x. So I'll write it like that. And then I can use the specific equation here and replace it. So I'm going to write 2, but instead of x here, I'm going to write -x. And then I'm going to keep going here and write -5. And this is just x here, but since I'm going to put a negative, I need brackets there as well. -x. And then I have my -3 there. And of course, I forgot my squared there. So if I'm going to work that out, I'll do it term by term here. We have to do this first, this power, -x squared. -x times -x is +x squared. So this actually just turns into x squared and the 2 there. Whereas in this second thing here, you have -5 times -x. -5 times -x is actually going to be, and this is important here, that this is going to be plus 5x, and the -3 stays the same. All right? So the squared term here, this didn't actually change. 2x squared is still 2x squared. The only term that changed sign was this one, where there's just an x there, right? So that's my equation of g of x. Now, second here, if we want to reflect it over the x-axis, this is actually a vertical reflection. If the mirror is horizontal, it's a vertical reflection. And if the mirror is vertical, it's a horizontal reflection. So if we're going to do a vertical reflection, what we need to do is we need to take f of x and multiply it by -1, or in other words, turn it into negative f of x. So I'm going to use something here for representing our transformed function. So I'm going to say let h of x equal our transformed function. So we need to take f of x, and we need a negative out front, so I'll do that. And then I'll do this just to emphasize that that's what we're doing. So then basically, we want our negative, and we want it to be the entire function negative. So I need to put brackets here, and then I have my function 2x squared minus 5x minus 3. And for that function there, that minus in front of the whole thing, I need to kind of distribute that minus, right? It's minus each of those terms. So what you're going to find is each of those terms is going to change sign. This thing right here was positive 2x squared, so it's going to become negative 2x squared when there's no brackets there. And this term was negative 5x, so if I distribute that negative, I get plus 5x here. And the last term is negative 3, so if I distribute the negative, I get plus 3. So that's my equation for h of x there, right? Now you could check your answer if you have graphing technology, a graphing calculator, or Desmos or GeoGebra or one of these graphing apps, and just confirm that if you graph the original and this one, that you can visually see on the graph that it's a horizontal reflection over the y-axis, and that this one is indeed a vertical reflection over the x-axis. Okay, in summary here, reflections. When you take the function f of x and you change it to y equals negative f of x, so on the graph here, f of x turns into negative f of x, that causes a vertical reflection. And another way you can say it is over the line y equals 0, or in other words, the x-axis. Again, I know that this can cause some confusion here because when you have a vertical reflection, it's over the x-axis, but the equation of the x-axis, the equation of that line there, is y equals 0, right? The places where y equals 0 are the invariant points. That's the line that doesn't change. And then if we take f of x and change it to f of negative x, in other words, if we replace x with minus x, then the graph experiences a horizontal reflection over the line x equals 0, or in other words, the y-axis. The equation of the y-axis is x equals 0 because that's where x is always 0. And then the very last thing there, reflections of a function result in graphs where the orientation, and I actually realized that I'm missing one thing here, orientation and or location may have changed, but the shape remains the same. The shape is the same, right? If you notice in those graphs there, this exact same shape, that was our original and our two reflected graphs. This one is kind of upside down or right side up depending on your perspective. Like this one opens down, this one opens up. It's in a different place as well, different location, but the shape's identical. And the same goes for the green one. This started here and the reflected graph is here. It's still sort of the same orientation because of the symmetry, but it's in a different location. All right, that's it.